So we are very excited to have Professor Aluffi coming from Florida State University. He will be talking about Segre classes and other invariant of singular schemes. Professor.
Thank you, Professor Rezul. I'm excited to be here. I was here several years ago. I think 2011 is where I was here.
The chalk is much better now.
The chalk is much better, yeah, I can tell. I do have a plan for what I want to say, but we'll see if I can stick to it. I'm taking very seriously Boyo's and Ivan's suggesting that I should not think of you as the audience. I should think of the audience as other people who may look at this after the fact through a video, and in particular, I'm really imagining I'm talking to a rather naive public who does not know these things. I'm quite sure that everybody in this room knows these things better than I do, actually. But I may, and I think Boyo wants me to talk about these things simply. I mean, there's a nice calculus of operations in intersection theory which makes some standard formulas more memorable or easier to handle, and that's more or less my goal. I would like to talk about that. In fact, as I was writing these notes, I got very excited when I was a kid and someone gave me a book. The title in Italian was La relatività con le quattro operazioni, relativity with 4 operations. After the fact, I learned that that was not the original title, but that stuck to me. Really, you could go through this book and learn some relativity by just using high school algebra. And here I have the feeling that I should call this intersection theory with the 4 operations, because that's the level I want to keep. I really want to think extremely naively about the general question of intersection theory and see where that leads me. And you will see that even by thinking very naively, you get the glimpses of very sophisticated definitions. In fact, that's my goal, to maybe give a very simple framework to think about things like Fulton-McPherson intersection theory, the little part of it that I understand, and see where that takes us. So in fact, I do have a plan for 3 lectures, but if I know me, I will not be able to stick to it. The first one should really be about Fulton-McPherson intersection theory. So I'll do some computations, which everybody could do by thinking very naively and just believing that intersection theory makes sense, that there is such a thing that as intersection theory and that it works. And I see that that leads to maybe motivation for the basic formula that defines the intersection product in Fulton-McPherson intersection theory. The main character here will be the Segre classes that appear in the title. And again, for the audience, I have in mind that this may be a mysterious concept. So my main goal is to just see that as soon as you start thinking a certain way, the definition of these objects becomes inevitable, essentially. So these become things that people, that I and others may want to look at. I don't think I'll be able to do any more than this here. And the second part, I would like to look at this again. Maybe I don't even exactly know what my main goal will be, but I will look at a certain calculus of operations in intersection theory. Well, calculus, about calculus. It's calculus. It's things you could teach to a calculus 2 class or calculus 1 class, or even before then. And see that that simplifies some formulas, or at least allows you to write some formulas in a very quick way, such as residual intersections. Residual intersection is one basic operation in intersection theory that allows you to attack rather interesting problems. And the third part would be the other invariants I mentioned in the title. So I will aim at talking about Chern-Schwarz-McPherson classes, Chern classes for singular varieties. But really, every other sentence will have the word Segre class in it at some point, because that's my main goal. Okay, so let me start with, as I say, let's think naively. I may know some algebraic geometry, so I know what a variety is. By the way, let me make a blanket assumption. I'm not going to be precise about hypotheses or where I do things or which field I do things. I'm just not very good at keeping track of all those things in real time. please, the blanket assumption is that you should take enough hypotheses so that what I say is true. About that. So, for example, I will probably work over C or maybe over an algebraically closed field of characteristic 0. Sometimes you will see why. Now, if I write 4, maybe you don't want to do that in characteristic 2. It's quite clear. So I may be much sloppier than this. You may see that at some point I'm clearly assuming that something is non-singular. Maybe, actually, if the audience here can help me and say, well, maybe you should point out that V is non-singular in this particular sentence. But anyway, let's think very naively and ask ourselves a very classical question. I want to know how many conics are tangent to 5 lines in general positions. This is a question. I should write a question somewhere, and I should put a question mark somewhere. And my distinguished audience knows that the answer is? No, that's a conics. It's much a harder question. This is a much easier question. Just 5 lines. 5 lines. The answer is 1. The answer is 1. So this cannot be a very complicated question. How do I know it is 1? Because I was there when the algebra geometry teacher in my class taught me about duality. You have projective duality sends conics to conics, smooth conics to smooth conics, to be necessarily more precise. So duality is just associate with say, my conic in P2, the set of lines that are tangent to the conic in P2, and if you just parameterize those lines, it's an easy computation to see that what you get is another smooth conic. Every smooth conic is dual to a smooth conic. So asking this question, if you want to be a little more technical, what the duality does for you is give you a rational map from P5 to P5, which you can look at interestingly. Why P5? Again, what are conics? A conic is the set of solutions of an equation like this. Did I decide how to index these things? Do I need to? I probably don't need to. Be careful about that. A0 x squared plus A1 xy plus A2 xz plus A3 y squared plus A4 yz plus A5 z squared equals 0. To give a conic means to choose these 6 numbers up to a scalar, so that's a P5, and only P5. One can think of plane conics as elements of P5. And duality sends that P5 to itself, to P5, only with a different interpretation. And that's very nice because then if you ask how many conics are tangent to 5 lines, by duality that's the same as the number of conics which contain 5 points. Right? The dual curve consists of the lines that are tangent to P2. So asking for this conic to be tangent to this line is the same as asking this conic to contain this point, maybe. And we are in P5. What is the condition of containing a point? To contain a point, I have to fix x, y, and z. That gives me linear relations between the AIs, among the AIs. Linear relation means hyperplane. This is the intersection of 5 hyperplanes. And as you know, 5 hyperplanes intersecting 1 point, 5 general hyperplanes intersecting 1 point. Okay, so that's fine if you were there at that particular class where the teacher talked about duality. What if you missed that class because you had something else? No problem, because you were at the other class where people were talking about the Zeus theorem. And so an alternative which you may think of is use Bezout's theorem. And I'm assuming that my audience is familiar with Bezout's theorem, because after all, if I just need to look at the conics which are tangent to a line, I can just figure out an equation for that. Conics that are tangent to a line L. What kind of object is this? I still have my conic over here. I'm trying to avoid the middle because of what people have told me right now. I have the conic over here, and it doesn't matter which line you choose, just to understand what the equation looks like. Let's choose the line x equals 0. That kills this part of the equation, leaves this much. So suppose L is the line x equals 0, then the equation becomes, I can just write it over here, a3y squared plus a4yz plus a5z squared. Those are the intersections of the conic with the line. You need this to be a perfect square. So I know how to express that. It's a4 squared minus 4a3 a5 equals 0. There we go. I discovered that the set of conics tangent to a line is a quadric in P5. That looks perfectly reasonable. So if I want to find the number of conics which are tangent to 5 lines in general positions, maybe let me call this quadric Q sub L. That will be the number of intersection of 5 of these. And Bezout tells me that that is, of course, 32. Right? I'm intersecting 5 quadrics. In P5, I should get 32. Now there's this kind of fancy number theoretic observation. 1 is not equal to 32. So something has happened, right? And okay, so let's see what has happened. Well, something very simple has happened, which I very carefully and quickly dropped one word. Hopefully, no, I didn't drop one word. I dropped it too many times. The question here should have been more precise. Not just how many conics, but how many smooth conics. And duality sends smooth conics to smooth conics. That's part of this data. So this argument, which uses duality, really relied on the conic being smooth. And it's part of the problem. Here, I did not write smooth conics. I was a little careless, and I'm careless by nature, as I mentioned, but not this careless, this much careless. I mean, there's a bound, a limit to that. And that's the problem. This is just an algebraic equation which puts in, checks all the things that are tangent to a line. Being tangent to a line means, as you saw as I was doing this computation, means intersecting a given line in a double point. So what you're thinking is that you're trying to count these kind of things. But this is a perfectly fine way to intersect a line in a double point. If I choose a double line, that double line will intersect a line in a double point. So that is the problem. Each one of these, so maybe I should put the problem somewhere, maybe I fit it here. The problem is each QL contains the whole set of double lines. So polynomials like this, which happen to be perfect squares themselves, the square of a linear term. Those things will be counted in, and this is a lot of stuff. This is a two-dimensional set. This is a surface. Right? It's 2 parameters, dimension 2. In fact, it is just a realization of the Veronese surface. So it's a very nice object. It's isomorphic to P2. It's not embedded linearly. It's embedded as an interesting surface, but nevertheless, it is a big chunk which is in this intersection. So let me rewrite that intersection, but with this in mind. So in fact, and this would require, of course, an argument, but if I take my QL1 intersection with dot intersection QL5, this intersection problem in P5, this is happening in P5. Mind you, each of these is a quadric hypersurface. These lines are general, so this intersect as well as they can, but that means, as you can check, a number of points. These are the things we are trying to count, union a Veronese surface. I don't think I can draw P5 very well. This is the picture of P5. It's the picture of everything, in fact, and we are having these very interesting hypersurfaces and so on. Well, there is a big surface here, a flat two-dimensional object, plus points, which are the ones I want to count. So what must be happening is that this guy contributes 31 to the Bezout number. Let's call this Veronese surface Y. It's not a good choice, maybe, but so what must be happening is that Y contributes 31 to the Bezout number 32. So that indeed, besides this, there's exactly 1 point left, which is what I was going to count. Okay, so that's the question. Can we understand how that happens? So just to write something a little more systematic, but I am not really sticking to any particular notation, but let me invent a notation. It's probably similar to notations used for this. I can imagine that I am in some variety, V, and trying to intersect things, x1 dot xn subvarieties, maybe. This is a very restricted, this could be schemes, I don't know. I'm intersecting things, and maybe I know how to compute an intersection product. I told you at the beginning, right? I'm assuming that we believe that intersection theory is there and makes sense, and try to figure out something about it. Maybe I have some information on this. In that case, I had Bezout's theorem that told me exactly what this was supposed to be. Well, suppose that, actually, let me change my mind about the order in which I'm saying this. Right, the intersection, the actual physical intersection of these things as a disjoint union of connected components, about Y disjoint union, a whole other bunch of components. And then, as I told you, right, we may be in a situation in which this makes sense, like the projective space. Bezout's theorem gives me what this, tells me what this should be. Well, it would be sensible to think of this as a sum of contribution coming from these guys. So since I pulled Y away, for some reason, I'll just write I, x1 dot xn, semicolon, Y. I'm almost inventing this notation as I speak. I think there are different versions of the same. It's not important. So I propose that we should try to understand this intersection product as a sum of contributions, each of which comes from the actual intersection. So in the case over there, I had 1 point and then this 31 coming from Veronese. And the question is, can I understand what this is? Some of you are cringing, I suppose, because I'm not saying where this is happening, or I'm not saying whether n is the dimension of the variety, whether AXIs are hypersurfaces. I'm reading my hands extremely much here. If you care, I don't want to make all those assumptions. This may just be subvarieties, n can be your favorite number. If the expected dimension is 0, then you can think of this as number equals number, but more generally, you should think of this as happening in some maybe homology theory, maybe in the Chow group. So in fact, I want to do this in the Chow group. And what is the Chow group? It's some kind of nice theory that you have in algebraic geometry, which takes over from homology, more or less. You think of this as a cycle modulo rational equivalence, if you know what that means. But you gain a lot already if you just think of the case that I was looking at over there. I have a dimension n variety, n hypersurfaces. I expect a number and that number should be written as a sum of contributions. Okay, now I want to attack this question. Any question? I could leave this alone. It doesn't matter. This is memorable, right? You will remember 31 for 10 years. So one thing that should make sense is that this contribution should be local. If these things are intersecting here and 100 miles from here you do something, that should not change the contribution of the intersection here. I mean, why should it? It should not. Right? So if I want to understand what happens here, I can really ignore what happens away from y. That's one way to put it. The other way to put it is that maybe I can try to understand this contribution by killing it, by killing y. That's the way we like to go about doing this. Try to do this, to understand this, to compute this, by killing it. That is, creating a situation in which that thing is not there. And there's a way to do that. So the idea would be blow up V along y. By the way, this is a scheme-theoretic intersection, right? If you want, when I write this, I'm really thinking that if you are near y, the ideal of y is really given by the sum of the ideas of the xi's. It's a very strong statement. This is not just a set-theoretic statement, it's a scheme-theoretic statement. So when I say blow up, I really mean the scheme-theoretic blow up, not just... That may make some sense later on. Blow up V along y. So here is the blow up of V along y, which dominates V. Y sits in here, and here I will have an exceptional divisor. This may not look very nice, because even if V is non-singular, it takes very little to get some awful stuff by blowing up V along a subscheme. If Y is also non-singular, then the blow-up is a nice non-singular variety, but in general, that's not what you expect. But I don't care. I can still imagine that intersection theory works pretty well, and let me make more assumptions. Assume the... Well, maybe I don't need to make the assumption right now. I want to call pi the projection from E to Y. And what I was trying to indicate earlier is that this part of the intersection doesn't care that you blew up along y. This has nothing to do with y. These guys are disjoint from y. So this part of the intersection should be the same. What about this part of the intersection? So that's one remark. The contribution to the intersection of yi should be the same. The blow-up looks around yi exactly as v looks around yi, so nothing should have changed. What about the contribution that I'm after? Well, what happens over E? This happens. After all, y is equal to x1 intersection xn near y. Right? Y is a connected component of the intersection. That means that if I take, this is where I should be waving my hands. Maybe I should make more hypotheses, but there's a very large class of situation when this will happen. The proper transform of the xi's will intersect the exceptional divisor in the, let's see, these are proper transforms, in, what should I write to the other side? No, what I'm thinking is this. This is x1, this is x2, they meet along y. In the blow-up, I have the exceptional divisor. This is proper transform x1. This is proper transform x2. They don't meet anymore. Oops. Yeah, that's exactly right. Once I restrict to E, that is, once I forget what happens away from y, the proper transforms don't meet. Right? If you think algebraically, once you do a blow-up, essentially, this is where I would like the xi's to be hypersurfaces. You're just pulling out the equation of E from each of the factors, and altogether, the pullbacks have to generate the ideal of E. So once you remove E, you have to generate 1, which means this intersection is empty. So this should vanish, should go away in the blow-up. let me write something. Let's see. This was essentially just advertising the definition I'm going to use for 5 minutes. So what should be happening is that if I take the original guys, is this what I want to say? Yeah, let's put it this way. Suppose I intersect the exceptional divisors and then push forward what I get. What I was trying to illustrate over here is that away from the exceptional divisor, nothing has happened. And on the exceptional divisor, I don't have anything anymore. So I managed to do what I wrote over here. I managed to kill the contribution of y. So I should get x1 dot xn minus this mysterious thing I want to figure out. So you see, now I have an expression for the contribution in terms of something that may allow me to do some computation. What made me hesitate over here is that by habit, I drop pullbacks, inverse images, things like this, because intersection theory is functorial enough that you don't need to take along those notations. So I'll be sloppy and write, first of all, for the computation I want to do in this board, assume the xi's are hypersurfaces. And what I write as xi tilde will be, you see, this is where I should be a little careful. Probably I should write pi upper star of xi, but I don't want to. In fact, it wouldn't be right. I will just write xi, by which I mean the inverse image of xi in the blow-up, minus the exception divisor. Okay, can you, no. I ask for forgiveness from my audience, but I will never remember to write the inverse image, even if I try to. So take this as a notation. And then what is going on over here? What do I need to understand? I need x1 dot xn minus push forward of x1 tilde dot xn tilde. In fact, let me do this computation formally and then push forward. After I push forward, my embarrassment of notation will disappear. So let's look at this. What is this? I have to warn you that I told you this is intersection theory with the 4 operations. A student of mine, a grad student of mine a few years ago, disgusted, told to me, this is high school algebra. That's exactly right. This is high school algebra. But this is what I want to do. In fact, I'm not good at high school algebra, so I'll do it for 3, maybe, or for 2 or something, and then we'll just believe that it extrapolates as nicely as you might imagine. Let's do it for 2. What is x1? Is 2 big enough to show what happens, or did I decide that 3 was necessary? I did it for 3 in my notes. Let's do it for 3. What's x1, x2, x3? Minus x1 minus e, x2 minus e, x3 minus e. Well, what happens is that one product will disappear, right? And then you will have a nice sign that will take care of e. And then there should be something that takes care of e squared, and the sign should be negative, I believe. And then there's e cubed. Does this look right? The second thing is that when you write just before the talk, it's so simple in the notes, but then when you're speaking in front of people, all of a sudden.
I think e squared will have a positive sign.
Let's see if he's right.
Negative sign.
I have lots of negative signs over
There's
here.
that minus right out, way out.
I think this is correct. The e squared will come with its own negative sign, which is not. For one thing, I know it must be so, right? So I'm not going to defend the computations. It has to be right. What's happening over here? It's clear what's happening, right? There's the second elementary symmetric function in the xi's, first symmetric elementary symmetric, zeroth symmetric elementary function. This is clearly what's going on. This is, let me just write it out. It's what notation, what's the standard notation for elementary symmetric function? How about E? R minus 1, x1 dot xn, E, and then minus E, R minus, is this right? I think so, 2, x1, xn, E squared, plus lots of terms. In the end, you get some sign taking care of E1, x1 dot xn, E, to the r minus 1, and the opposite sign will take care of e to the r. So here, ei is the ith elementary symmetric function. Okay.
R is equal to n?
Yep, very likely. So there was no r before, right? It's n. Sorry. N, wherever I wrote r, I should have written n, and thank you, Ivan. I think r is n, yes. What's the next step here? I mean, how can we make progress? There's a very simple observation which might occur to you, might not occur to you. First of all, I mean, of course, by the way I got it, every term here has degree r, n. It was r in my notes, as you might guess, right? Well, this is the same as the degree n term in something I can write a little more concisely. If you are like me, you don't want to keep track of this notation. And here it is 1 plus x1, 1 plus xn, and then e minus e squared plus e cubed minus dot dot. Of course, you will get, if you care, you get all the way to plus or minus e to the n. Do you agree with me? There's lots and lots of other stuff, but the degree n term does exactly this, right? What goes with e cubed? Well, you look at the degree n minus 3, you can get out of this. It's the third, an n minus third elementary symmetric function in the xi. So why is this progress? I still need to push forward so that you are less disturbed by my not including the notation over here. This is progress, but the progress needs to probably be highlighted more somewhere on the board. Do I need much of this anymore? Maybe let me leave it alone in case I do. So the conclusion is that this contribution of y to the intersection of the ni's apparently is this, right? It's the push forward of this expression. So this is, you see, I'm assuming I'm talking to a naive audience, but I'm also asking to believe things like this business with notation will not matter. Once I push forward, things clean up. I don't need to worry about this. That's what the projection formula does for me. So it is the term of dimension of degree n in, let me just write it out. It's, in fact, let me invent a notation for that. Apologies if you're attempting to take notes. Let me just write what I've written over there, but including the push forward. The push forward goes here. E is not the inverse image of a hypersurface, so I really need to keep track of it. And then you take the term of degree n. Okay, I've written something that is maybe a little more appealing, especially because I'm assuming that the xi's are hypersurfaces. Hopefully I've not forgotten to say that. Yes, I have not. So I know what 1 plus x I should be. It is the Chern class of the normal bundle of xi in my variety. So what I'm writing over here is really a funny thing. You are taking the Chern class of n x1v multiplying by the Chern class of n xnv, and then hitting this with something. And here comes the definition. I need a name for this. I don't want to write pi lower star of e minus e squared all the time. This is the Segre class of y in v. Definition. This is the Segre class of y in v. I need to do this operation, and then I need to take the term of degree n, which would correspond to the term of expected dimension in the intersection. Okay, I think I wanted to leave this on the board because I think it's pleasant to see still the main characters over here, but I can probably get rid of some. This was the observation allow me to do the computation, so I can go. This can go. Maybe in the interest of clarity, let me just officialize the definition. The Segre class of V of y in V. I'm assuming that y is, in fact, I can assume it's a subscheme of a scheme. There's no real restriction here. So. Is pi over star of e minus c squared plus c cubed dot dot. With this notation, E is the exceptional divisor of the blow up of y in V. Okay, and what I've written over there is that the contribution of y is a certain combination of normal bundles. I'm rewriting what I've written, just why not? I use this term all the time. This is where I take a cohomology class and use it to hit a homology class. It's just notation. Don't hold me responsible to it. Questions? Comments? So what happens in the case of conics? So I was inside, yes, any question? I had V P5. I had quadrics, so the Chern class of the normal bundle of a quadric in P5 will be 1 plus 2 times H, where this is the hyperplane class. And what I've discovered is that the contribution of this Veronese y should be equal to, well, take that Chern class to the 5th power and hit it with this mysterious Segre class in P5, and then take the term of dimension 0, because that's the expected dimension in this case. So is this progress? It is progress if I have any way to compute this guy. But you see, the underline, the point I'm trying to make is that if you can compute Segre classes, you will be able to approach these kind of problems. The computation I did was reasonably general. Whenever you run into a situation in which you have a nice parameter space and you intersect things and you want to evaluate a certain intersection, maybe intersection theory tells you the global intersection, but you recognize that there's a place that you want to eliminate from your intersection. Well, to evaluate the contribution of that bad place, we'll do something like this.
Is that what's supposed to come out to be 31?
Let's see if it does. No, I still have a little bit of time, and I'll get it by talking about this a little more. Before coming back to 31, I want to look at this definition, this computation, just a little harder. So I want to shift the focus a little bit. So this is a little shift in perspective. And this is where, for example, I would like V to be non-singular, but people who know what I'm sweeping under the rug will forgive me, I hope. Shifting perspective, rather than looking at, then intersecting x1 dot xn in V, consider the intersection of x1 cross dot cross xn with the diagonal in V cross dot cross B n times. Right? What does it mean for a point of this to be on the diagonal? It means that all the coordinates, all the components are equal, so that means it's in the intersection. It's set theoretically the same set, and if you do it otherwise, you're just as happy. So really, let me draw a diagram which kind of captures what we have done. the diagram looks like this. You have x1 cross dot dot cross xn going to v cross dot dot cross v n times. We have the diagonal over here, and I'm taking a fiber square and putting the intersection here. That intersection was the disjoint union of the, what was it? I think I wrote y disjoint union. But this was the decomposition as a connected component. And this formula I keep taking along. I'll get back. I promise today that I will get the 31 before we are done. The formula I've written over there is really taking the Chern class, so the contribution of y turned out to be equal to the Chern class of the normal bundle of this whole product in V cap, the Segre class. You see, up here, this is a copy of V, and this is just the same time as before, so nothing has changed, really. The reason why I want to put it this way is that then it allows me to advertise the definition of intersection product in Fulton-MacPherson intersection theory. So more generally, much more generally, right? Here I was assuming that the xi's were hypersurfaces and so on and so forth. Here I'm not going to make any such assumption. I'm tempted to recycle the same letters with a different meaning, which usually is not a good idea. Maybe I should not do that. Let's not do that. So suppose you want to intersect B and letters Z in W. I'm trying not to use the same letters I've used a moment ago. What are these things? Say that W is a variety. You can do better than that. I say that Z is a subvariety. Since I'm not giving the most general story, I don't need to try to be ambitious with my notation. Something I have to require from B inside W must be a regular embedding. So locally it's given by the number of equations, so to speak, in case you have a normal bundle of B in W. And then look at the diagram, which is pretty much like this diagram. This plays the role of B that goes into W. If I'm using the notation correctly, I have 0 here, fiber square, so here I just have B intersection Z. And if you open Fulton's book, chapter 6, section 6.1, I believe, then you will find the formula such as this: B dot V equal, take the Chern class of the normal bundle of B in W, and cap it with the Segre class of B intersection Z in Z. And then look at the term of expected dimension. Okay? So if I have been successful, then you see that that's not unreasonable. This is exactly what I've done over here. And this was coming out of high school algebra, so to speak. Right. Normal bundle of the horizontal side, bottom side, and Segre class of the top side. It's exactly the same thing. Okay, and if you have y as welcome to the twilight zone. If you have y as a connected component of the intersection, which is the situation I've been exploring, then the contribution of y is just the same thing. C and B, V, W, Segre class of y in Z, terms of expected dimension. Okay, so one of my goals for today, not the only goal, was to motivate this formula, and you see how you can view it as coming out of just a little game of formal expansions of polynomials coming from a blow-up. This can go. Now, of course, I had to start making choices about what I can say today and what I cannot say today. I had a couple of paragraphs over here. Let me talk my way through them rather than trying to write something very careful. But no, you should have a maybe better perspective on why this is the natural definition. The idea maybe is that if you're trying to intersect this guy with this guy, well, it should not matter that what happens far away. Again, you should be able to take a big magnifying glass and look in here, which means you should be able to replace these things by some kind of linearization. This thing will linearize to its cone, while this guy, which was a good guy, will stay good. So I should be able to linearize things without changing the contribution to intersection. So if I linearize my situation near y, I should not change the contribution of y. And this is what is happening here. So maybe I can write something by some process which I'm not going to talk about in any more detail than this. By some kind of linearization process, you replace the embedding of B in V with the embedding of the zero section of B inside the normal bundle to B in V. So in practice, you are replacing V with the normal bundle of B in V, at least near Y, right? Near Y. And you're replacing Z with the normal cone of B intersection Z with Z. So this reduces the problem of understanding the contribution of Y to understanding a simpler problem, something that happens in a vector bundle, for which the intersection theory is somewhat transparent.
V is W.
Ooh, V is W, absolutely, thank you. Thank you very much. And so if you, I guess, look up Fulton chapter 3, then you will find description of the intersection theory necessary to intersect with the zero section in a bundle. And applying that formalism leads you directly to this. So that may be a better or a more conceptual explanation of why this is the right definition. It comes from a linearization process. There's the deformation that takes you from being inside V, from this diagram to an analogous diagram in which everything has been linearized. This has been replaced by the vector bundle, by the embedding of the zero section in the vector bundle, and this gets replaced with a cone, and then doing the operation gives you this. Why is that, by the way? I probably can use that to motivate, yeah, again, to understand this maybe a little more conceptually. What was this business? The Segre class has disappeared. It was the push forward of E minus E squared plus E cubed minus dot dot. What is this? And for one thing, what is this? What is the cone? If you're not familiar with cones, maybe this doesn't tell you much. But there's a nice observation that whenever you have this blowout diagram I had before, I was blowing up Y in V and back to Y V's and stuff. So here's the blow up. And here's the exceptional divisor. There's a fact. The exceptional divisor is canonically isomorphic to the projectivization, which I use this symbol for the lines in projective space, in vector space if you care, of the cone of Y in V. So if you want, you can take this as the definition of the cone. The cone is at least the projective cone is this. The projective cone of Y in V is the exceptional divisor in the blow-up of Y along V. And together with this, there's a realization of what O1 for that cone is. It happens that E, if you take the line bundle of E and you restrict it to E, what you get is O of -1 of this cone. Again, for my audience, if you're not used to these words, then they will not make much sense. But if you're used to some of these words, I hope that I'm filling in the things that I'm missing. Then what is this E minus E squared plus E cubed minus dot dot dot? What one is doing is really pushing forward a sum for I greater than or equal to 0 of the first class of O of 1. That's why there are all those signs in there to the ith power. cap the class of the projective cone. And this is the official definition of Segre class. Again, if you open Fulton's book, chapter 4, I suppose, then you will find this as the official definition. Almost, I don't want to, God forbid, I don't want to say something wrong.
Call it the inverse of the first term.
Excuse me? Why don't I want to just write CO of 1 negative 1 inverse? Something. Yeah, well, yeah. By a well-known theorem, this power series is, and in fact, I use that kind of notation a lot. I can just write this as E over 1 minus E, I suppose, plus E, which will be the inverse of the total Chern class. Yeah.
And what you call a fact is actually essentially the definition.
Yes. Yeah, I mean, yes. It depends on which you prefer as a definition, the spec of graded ring or yeah, I agree. This, there can be some discussion of what fact means in this sentence. In any case, I just wanted to reproduce what you may find if you open Fulton's book. This is what you find, and you find this as an observation. Among the things I'm not saying is that I'm secretly assuming that this is not equal. Otherwise, there should be a little correction to be made here. Why am I saying this? Because if you're familiar with some of this business, then you may recognize that that is, again, is it the fact or is it the definition? I think in Fulton's book it is the definition of Segre class of E. Note, E meaning a vector bundle. If maybe I use curly E is a vector bundle, then the Segre class of E, meaning the inverse of the Chern class. Why can we take inverses? Because we're not working equivariantly, I suppose. So this is 1 plus a nilpotent. You can always take the inverse of 1 plus a nilpotent. This Segre class of E is defined to be, or proven to be, if I call pi the projection from the projectization of E, that formula, Segre class of E is pi over star of summation C1 of O1 to the I cap P of E. Why am I saying this? Number one, to connect with things that you may have seen somewhere else. And number two, because that gives me a tool to compute actual Segre classes. So, as a corollary of this observation, so here's one property of Segre class, property of Segre classes that you discover by staring at this formula. I'm serious, you can take this as a definition of Segre class. That's exactly what Fulton does in this book. And then you can define the Chern class or vector bundle by inverting this and proving that it has the properties you assume. But look at this and that. They are the same gadget. The difference is that here I'm doing it to a projective cone, here I'm doing it to a projective bundle, but that's just at this point a matter of notation. One property of Segre class, if Y in V is a regular embedding, then that formula tells me that I'm computing the Segre class of the normal bundle of Y in V. Let me call it Chern class inverse. The Segre class as the inverse of the Chern class of the normal bundle of Y in V. And again, I like this notation capping against Y, so the corresponding homology class. I'm not sure I did such a good job with that. I hope that here I was pointing out that this definition I used comes from here, and here I was observing that in the case in which your cone is a bundle, then what you're doing is a familiar operation from the theory of Chern classes. In particular, I get that the Segre class, this thing I'm trying to compute, in this particular case is just the inverse of the Chern class of the normal bundle. Do I know a case in which that applies? How about this? This is a case. This is a case in which Y is regularly embedded. Is this trivial? It's not trivial, because what you would have to check is that the scheme-theoretic intersection of these quadrics, which contains Y, is really Y, not some kind of fancy important structure on Y or whatever. But that is the fact. It is so. No. So let me just, in this case, Y is isomorphic to P2. Really, the scheme I need to worry about is isomorphic to P2, which is embedded to P5 by the second Veronese. Now let's do computations. I mean, the hyperplane here I will call H. That's the class of a line in P2. The hyperplane here I called big H a moment ago. How do I go from big H to small h? That's what this information comes in. Second Veronese means that the components of this map are quadratic polynomials. So if I pull back h, I get twice h. The pullback of h is 2h, which allows me to do this in Y. It has to be 1 plus, well, 2 big H becomes 2 times small h, to the fifth. And what I've learned a moment ago is that what I need to put over here is this class. Oops, so I have to compute this class. What is this? Let me, maybe. Excuse me?
There should be an inverse.
Absolutely, thanks. Let's compute that. What's the Chern class of the normal bundle of Y in P5? I'll just quickly write a bunch of stuff that you can verify if you want. What's the normal bundle? You have to remember the sequence. Ty goes to TP5, Y to the normal bundle of Y in P5. If you know something about Chern classes, you know the Chern class of this is the Chern class of TP5, and there's a formula for that. I'm pulling back to Y, so my big H becomes 2H. And the Chern class of Ty is the Chern class of a projective plane. Now, this is really mindless high school algebra, I suppose, or maybe calculus algebra. No. I did this, I promise, and I got 1 plus 9h plus 30h squared. And I don't need to go any further because the square of a line is already a point. The cube is 0. I could have just done this right away, I suppose. The inverse is the inverse of that. So you can eyeball that it's negative 9h. And the other thing is 81 minus 30, if you think about it. So that's what I need to put over there. And no, we know how to take the fifth power of a binomial. We know if we look it up, I suppose. 120h plus 160h squared. And here I have 1 minus 9h plus 51h squared. Y is P2 after all, so let me just write this too. Dimension 0 means degree 2 in Y. So now your task is to compute the degree 2 term in this product, and it just happens to be 31. Is that right? It's 51 minus 180 plus 160, so that's taking 51, 20 away, that is 31. Okay, so it does work.
It's just a coincidence.
It's a coincidence, yeah. I verified this coincidence many times in many cases. Unfortunately, I see my time is up. Of course, I'm about 1/3 of the way through, but okay, so it looks like this is a good stopping point unless other questions.
Any questions?
My only question is, were you making up which sections those were references to in Fulton's book? I almost got up and got the book to see if you were getting them all.
You can double
right.
check. It's recorded, so no, you see.
He actually knows.
Well, I figure, but still. Is the motivation, do they motivate the definition of intersection number as well as you did? I mean,
No, much better, of course. I mean,
well, I mean, yours is very down to earth, and you see why it counts intersections.
Right.
people leave out.
Yeah.
Okay.
I don't remember
There's some historical notes in
they're
Facebook.
doing that.
Actually, I'm extremely bad with history, and that Steve is extremely good at history. I suspect that Segre came up that did this. Maybe that's what he must have thought about. And if Segre classes are called Segre classes, it's because Segre came up with this nice combination of E minus E squared plus E cubed, and I suspect that he did exactly the computation I just did for you. I should, no, someone should check. But yeah, that must be it.
I might add
Yes.
a comment
Please.
about your imagery at the beginning of killing Y by an explosion.
Yes.
That's the wrong way to look at it.
Okay.
Blow up is used in the sense of magnify, right?
Yes. Indeed,
So,
that's very
right.
true.
So what we are doing is looking at what's going on in the neighborhood. Infinitesimal to the first order, that's your linearization.
Yes. Precisely.
Actually, I think it's in between magnifying and exploding. I think it's spreading out. It's a spreading out. So it both magnifies
Yes.
and it's like an explosion that makes this cloud of
Limited explosions.
The language is kind of interesting actually, because originally I think the Italians used dilatazione di base or something like that, which
They use what word?
dilatazione di base, which makes perfect sense, right?
which means, I'm sorry, which means?
Which means well, dilation
Dilation.
of the base. The base is what you're going up. But then the French called that éclatement. That must be
It's
the
because
right
of
translation. And then the
Napoleon.
Italians translated éclatement into scoppiamento. So now in Italian you find scoppiamento, which is the explosion business. So,
Hironaka introduced the term, I think, blow up.
No.
okay, I don't know the English story of that. But, okay, blow up is correct, of course, for magnifying. But I'm curious about the Italian path that took from dilatazione di base, which was blow up in the optical sense, to scoppiamento, which is blow up in the explosion sense.
Did he say blow up in English, or did
Yeah.
he say something equivalent in Japanese?
No, it was in his paper. Because the theory of blowing up was not at all well developed at that time. For example, the universal property and all these things.
Well, they used the, Zariski used the term mono.
Monoidal
Monoidal, there we go. And the Gothic called it a dilatation, which is close to dilation.
Right, right.
Any more comments? Let's thank Paolo again.
Okay.